All right. Hello, everyone. I hope I'm audible. Uh, just give me a second before we begin. Let me just quickly check if people are able to see this on YouTube and LinkedIn. All right. I think we are live. So what I'll do is, first of all, I'll start with a quick introduction. My name is Prateek Singh. I'm a founder of Ganak.ai. I was working for LinkedIn for almost 5 years. I have over of 13 years of experience working in tech. Most of my work life, I've been primarily working on software and a lot of infra. So today I'm going to talk about building RAG applications in Azure. All right. So with this, let me just quickly switch my view to the code editor. So today, primarily, we are going to talk about retrieval augmented generation. Three things, retrieval, augmented, and generation. That's very obvious. But first of all, before even we begin, we should think about like, why do we need RAG if we have things like a large language model, even like small models? Why do we even need RAG for our use cases? So first and foremost is what is RAG? RAG is a framework that augments general knowledge of a generative AI LLM. What I mean by that is basically your LLM is trained on a huge like amount of data, humongous data sources. But the thing is, uh, it doesn't have domain specific knowledge. So for example, if you ask question about like an enterprise knowledge, question related to enterprise knowledge or what you call it, for example, internal wiki. So you have written extensive wikis in your enterprises, but your LLM doesn't understand that. And since it doesn't understand that, it's not able to answer that well as well. So you need some mechanism to make sure whatever response an LLM is generating, it is grounded in domain specific knowledge or actual facts. So this technique is also called grounding. And this overall process of retrieving the domain specific knowledge, augmenting it with existing understanding and generating an output is called retrieval augmented generation or RAG. All right. So with this, some quick pointers. RAG is a framework, obviously, and it is used to add additional data to LLM because it's very hard to retrain LLM every time you have some additional data. So you need something which can quickly fetch data for you, augment it in LLM's understanding, and so that LLM can easily generate an answer for you. So with this, let's move ahead. This is how an entire RAG process will look like. So on the top, you have these documents. These documents are converted into chunks and then fed through an embedding model. So let's not rush into what an embedding model is. We'll quickly cover it later. But this is how it goes through this is how the chunks are formed, goes through an embedding model, which is a trained model to understand what different modalities of data is. It could be text, images, and everything. And based on that, it can generate some embeddings. We'll talk about more like what an embedding is. But this goes through an embedding model. The embeddings are generated and saved in a vector database or a vector space. Similarly, user query is also generated, uh, goes through the embedding model. The embeddings are generated, and this is the query and the actual documents which are chunked and then embedded in the vector database. They are actually used to identify how closer are these two together. So, for example, if I ask a question, in all the chunks which are embedded in the vector database, how closer they are, based on that similarity search, the relevant chunks in the documents are retrieved from the vector database, and LLM now understands and basically generates this. So the next step obviously is, after retrieving all the chunks based on their embeddings, which are closer to each other, which are similar in meaning. This is basically passed to a prompt template where it has user query, it has chunks of documents which are identified by similarity search, and then these two are augmented together and then fed to LLM. So once the LLM has the user query, has the chunks which were retrieved using semantic search or similarity search, it can basically generate a proper grounded factual response to you. So this is on a very high level what a RAG is and how things work. Moving on, we'll quickly see like how we can first of all prepare our data for retrieval augmented generation. So obviously, we could have like a lot of unstructured or a structured data, which we have to basically create different chunks or basically split it into smaller consumable size. So you can see on the left hand side, we have image, documents, videos, and audios, or any kind of data which we can have. We can have JSON files or whatever. Then there are models which are embedding models. These are pre-trained models which are available. You can check on OpenAI. There is text embedding ADA, the new models. You can also check on Hugging Face. There are a lot of like competent models available uh, for different modalities which can understand your data and create a vector embedding based on your data. So whatever chunks are going through the embedding model, it creates a numerical representation of that data. So if I write hello, that hello could be converted into a series of integers. So for example, you see like 0 0.1, 2.5, 0.98. So this is the dimensions of that data, and they are basically created in form of array or a string, which then gets plotted into a vector database. So these whatever numbers you see, these are just one point in the vector space. So you see this vector database. These are different. All these points together form one coordinate in this vector data space. We'll talk about more and see the relevant live examples of what this vector database is and how we can locate our data. But for now, just understand whatever chunks you have, you can convert that into a array of integers, and that array of integers is a coordinate in a vector space to use to identify the meaning of whatever chunk you are passing. All right. So with this, we have some like very high level understanding of like what RAG is and how we prepare our data. What is an embedding? What is how we are going to insert in vector database? We'll talk about more on this. But before we even begin, uh, there is some prerequisite which you need to do. I'll quickly switch to uh, my browser here. Just give me a second. So what you have to do is, first of all, you have to create an Azure AI Hub, basically an Azure AI service. You can come to your Azure portal. You can create a new resource. You can search for Azure AI service. I'm not going to create this, but I'm just quickly going to show you how you can do this. So you can go ahead and create this Azure AI service. And what this will do is it will let you create an AI hub. So you can use the various tiers. You can, based on your location, you can choose your location, service name, and all those details. So once you've created an AI hub, you'll get something like this, an AI Foundry project. You can come on AI Foundry. You can create different projects. So I've already created one. So you can click on Create New. You can choose an AI Hub resource or AI Foundry. I have used AI Foundry here, and I've created a project already. So once you have created your Azure AI service, you'll get a resource name like this, and you'll have API keys and all those things. And if you want, you can come scroll down to the bottom here, and you see these. There is an option to create models as well. So all the base models, all the like competent companies which we have created these base models are ready to be deployed for your enterprise in Azure portal here. So you can, or what you can do is you can come here, you can select a deploy base model, and you can choose a model. For example, GPT-5 is the most new one, or whatever the model available. I can click confirm, and basically it takes me to the page which will let me create this model for me. So for just sake of simplicity, we have already created some models. So this is my Azure AI service. I have created a couple of models here, which is some text completion models like GPT-4o1 Nano, and some text embedding 3 and text ODA model, which we are going to use to generate embeddings using this Azure AI service. So once you have your models ready, we can just quickly switch back to our code editor, where we'll have to create an environment variable, which you can see here in .env file. And if you guys want to access this code repository, I'll just quickly open this view where you can just quickly grab. This is an scan. There is a QR code available in this view. You can just quickly scan this, and it will just scroll down. Once you go to the link, scroll down a bit. There is a demos and presentation section where I have links to all these demos, which I basically demo. And you'll get the code samples, you'll get the slide decks and everything available there. All right, so stop the video and grab this QR code, and you are ready to go. Uh, all right, so once we are all set, we have our Azure OpenAI service created. We have created the model names and everything. We are just going to create an environment variable in my uh, repo like this. And once we have this ready, I can quickly switch to my Jupyter notebook, which I have here, which is for preparing the data. So this is nothing fancy. I'm just fetching the environment variable which I have created. This will load everything which I want. There would be some authentication happening. Make sure that you log in through Azure CLI, because it will fetch your credentials and get the bearer tokens and everything. So you can quickly do that by running AZD auth login and everything. So that's a pretty easy process. Just make sure that you are logged in. And once you're logged in, you are ready to create using the Azure OpenAI SDK. You can easily create an OpenAI client. So I'm going to run this, and this will load all the environment in the project. All right, so I have the environment ready. I have a client ready to call the endpoints for the text completion and embedding model. Now I have this. Now have some data with me. So for example, just for sake of simplicity, I have this movies.json file. So this is a big JSON file, which has like a list of a lot of movies, like we can see Shawshank Redemption, Forrest Gump, Lord of the Rings, and many more. It has year, genres, plot of the movie, and everything. So we are going to use this to basically create smaller chunks, then create embeddings going forward. So I've simply loaded the file in my repo, and I'm just creating chunks. You can choose the chunks how you like it. You can choose a chunk size. There are different strategies how you do chunking, but for this demo, we are not going deep into chunking strategies. So basically, you can define the chunk size. You can define if you want to have overlap in your chunks so that the context is not lost between two chunks when the embeddings are created. So you can do a lot of strategies around this, but very straightforward and simple. What I'm going to do is I'm going to pick every movie and going to treat it as a chunk, and each of these chunks would be just then passed to a embedding model, which we have created in Azure AI service, and to create an embedding out of it. So I'm just loading all these chunks. So you can see here, I have different chunks present. So chunk one is first movie, chunk two second, and then going forward like this. So we have total of 25 uh, embeddings here. Right. Sorry, chunks here. So I'm going to just use all of these chunks to just create an embedding. So what I'm trying to do is I'm just using the OpenAI client. I'm using embeddings dot create, passing the name of the model which we had in this environment file, and the model name is text embedding 3 small. This is the same model which we already saw in our Azure portal, which you have already created. You can also go ahead and create one for you. And this model is basically used to create embeddings. And once I run this, you will see in a few seconds, it will create embeddings out of each of these movies which you just saw on the top. So it takes a couple of seconds and we are not in rush, so we'll wait. So yeah, so it is done. And we can see clearly that it created 25 chunks out of all the movies we passed. Used the for 25 chunks to create embeddings. And just for sake of understanding, I've just printed the first chunk. And you can see that each of these chunks are created into embeddings, which are just a array or a series of uh, integers which you have. Right. So this is created, but one funny thing which you'll see and we should I think understand is when I see the length of each of these embeddings, I get this specific number, which is 1536. So what is this number first of all? And how many integers do we get? So this number basically represents the number of integers which you are getting out of the embedding model. So each embedding model is designed to return embeddings in a specific set of integers. So each integer here represents a dimension. So for example, if I talk about king, maybe like height of the king is could be one dimension, or the color of his cool robe is one dimension, and like his hair length, his weapon, or whatever, his aura is one dimension. So there could be n number of dimensions of any specific chunk or a word or an image. So these integers are just dimensions which are returned, and each model have specific dimensions which they return. So this since we use text since we use this text embedding 3 small, this returns to like 1536 dimensions or 1536 integers for each embedding. So now we have all the embeddings which we needed. Now we need to store these embeddings. So we have this embedding, but how do we store it? So Facebook have this the open source library called Facebook AI Similarity Search, which is FAISS, which is an open source open source project, and it is used for similarity search. It is also used for vector clustering and all other use cases. But for sake of simplicity, what we are going to do is we are going to use Facebook AI similarity search to just create a vector database for us. So what I'm going to do is I'm just going to normalize and flatten my embeddings all with what I've created, and I'm going to write it to a vector index. So once I run this, it will create a file like this, which I cannot open obviously because this is an index file, which stores all the embeddings. But we'll take a look into this later. So with this, our data storage completion is complete. We were able to chunk our data, which is the movies.json file which we had. we were able to create embeddings out of our data, which is like a semantic meaning of that database, sorry, that data or chunk. And then we have stored it into a vector database or index, which can then later be used to fetch the data or embeddings from. So with this, we'll move to the next part of this retrieval augmented generation demo. And this part is the retrieval part. So let me just quickly scroll to the top and feel free to drop any comments if you guys have. I'll try to answer them from the chat both on YouTube and on LinkedIn. All right. So now, before we even understand what retrieval is, I think the more important thing is to understand how we will retrieve the data. So we created embeddings, and those embeddings are now stored in a vector database. Uh, but how are they stored in vector database and how are they fetched? So the retrieval part is very important in this use case. So what I'm going to do is quickly talk about uh, what is a cosine distance, the similarity, and all those things. Here's a 2-minute video. If you have scanned the QR code in the beginning of this demo, you should be able to see a quick small video to understand what cosine similarity or a cosine distance is. So you see this three-dimensional vector space on the screen, and you see there are two vectors going on. The vector on top is XYZ, X1, Y1, Z1, which is for A, and then B is for X2, Y2, Z2, which has meaning for B. This is nothing but a vector which is plotted with using three coordinates in a vector, three-dimensional vector data space. And these two meanings or whatever words or chunks we have created in a vector DB, they have specific coordinates. And these coordinates, once plotted in the vector database, they'll have some angle in between. And this angle basically decides how closer they are to each other. So if you have like a very like a small angle, then the two meanings are very close to each other. As and when the angle uh, expands, the meaning is like very dissimilar or totally unrelated. So I'll show you another example here. And here I have king and queen. Right. So king and queen are closer to each other because they are both royalty, and you can see they are very close to each other. And then we have a man and woman. So these kind of things are plotted into vector database, and based on the angle, we define uh, how they differ into like from each other in terms of semantics or in terms of meaning. So you can see that king and queen are very close, but they differ by gender. You see them, man and woman are very close, but they also differ by gender. And then man and king a little far, queen and woman a little far, and these two clusters are a little far as well. And these two are related in terms of royalty. So this is how different meanings are derived from the vector space. And just to explain the point of in terms of like if two vector spaces are very close to each other, the cosine angle between them should be 1. So the closer it is to one, the closer it is to one, the meaning is like very similar to each other. And as and when this cosine angle expands or increases to -1 to 0 and -1, they become like not related, dissimilar, and very dissimilar. So this is a quick representation of each of these cosine angles and how this cosine similarity plays the role in the retrieval of an information. So for example, if I query something like king, it should be able to retrieve queen as well from the using the cosine similarity. So whatever data has the smallest angle should be retrieved using cosine similarity, and then we'll use it further in the generations. So this is basics of how cosine similarity is used to uh, get meanings which are closer to each other to fetch the based on embeddings from the database vector database and then feed it to the later steps. All right, so let's move ahead with the demo. Again, we'll just initialize our environment variables and create a client here. And just for the sake of understanding, what I am doing here is I have two sets of sentences. So one set is just the same sentence four times. The new movie is awesome. And the second side is uh, sentences which are changing and becoming like more garbled. So you have the new movie is awesome, which is same as the first sentence set. Then it is gradually changing to something which doesn't make any sense. So what we are going to do is we are just again going to use an embedding model, create embeddings of both of these sentences. So I'll pick movie one, first sentence, and then first second sentence of sentence two, and then compare each other, and so and so forth. So if I run this, you will see each of these sentence, the embeddings would be created, and embeddings are going to be matched using. We are going to get a cosine similarity of each of these embeddings. So if you see, we are going to fetch the cosine similarity. I'm just using the SK learn metrics SDK here to get the cosine similarity between these data. So I have sentence one, and when it is compared to sentence two in terms of cosine similarity, you guys see that it is one. And we discussed on top that things which are very similar would be one. And as and when the meanings are not closer to each other, it basically drops to zero or goes to -1. So you see that as and when the data is the not matching to each other, the similar cosine similarity is dropping, right? So the new movie is awesome with this garbled data is coming with something like 0.06, or if we have like a very different data, it will may go to -1 as well based on this representation. So this is how we understand how things are similar in meaning and using embeddings and cosine similarity. And this is going to be used as our retrieval mechanism. So to retrieve the data, I'm going to perform a similarity search again with cosine similarity on the vector database which I created earlier in the preparing the data step. Right. So again, I'm loading my movies.json. I have a small query here which is a story about prisoner. I want a story about prisoner, and I don't want to go into this the detailing what I'm trying to do here, but I'll simply run this and I'll quickly show how things look like. All right, so yeah, so it ran, but I also want to show you that I'm just fetching the embedding, the index I created earlier for the embedding movie title embeddings in cosine. I'm just reading that index and which already has all my embeddings in the vector space. And I'm just going to use my query and create an embedding out of my query and then do a similarity search. So if you understand here, I'm doing an index search here. So I'm using my query and I'm also using the index. So what I'm trying to do is basically convert my query to an embedding and then use that embedding and see in the vector data space whatever movie embeddings you have already created, what is closer to the meaning of my query, which is a story about prisoner. And I'm just using the cosine similarity. I'm going to fetch some top results. So I'm fetching top five result here, which is k equals to 5. And once I have fetched everything, you will see this is what I see. So if you see here, I got a story about a prisoner. I got Shawshank Redemption, I got Pulp Fiction, and I got a few other movies. But you see the cosine ratings are very low. This is like zero point 0.3. This is like closer to zero, but I wanted something like zero point 0.7 and above. We should be like similar to my meaning, right? So this is happening because once we created the embedding, so I'll quickly jump to the embedding, the chunking and embedding creation step. You see, this is the structure of my JSON, right? This is basically the structure of my JSON. So this schema is very different from when I go to the retrieval part again. The schema is very different from this query. So that is why once the cosine similarity is done, you see they're a little far. They're still giving some results, which is kind of matching with my query, but they're still a little far. So now let's do one more thing. Just for understanding, I'll just create a query which is very similar to the structure which I used for chunking. So I'll just directly pass this Forrest Gump and all those things, and you see now the results are much closer uh, to what I wanted based on cosine similarity. So this is again like how chunking is done. There are a lot of strategies. You should be aware what model you used, what chunking strategies you use to get a proper result. If not done properly, you may observe some issues going forward. All right, so now we understand how we retrieved like top five movies based on cosine similarities. Now let's do one more thing. We talked about vector data space, how we are getting all these similarity using cosine similarity, how we are getting all this data. Let's also understand how this looks into a vector data space. So what we'll do is we'll visualize all these vector embeddings and distances in a 3D vector space. But if you can just recap very quickly, we talked a little bit ago. We talked about that we have total of 1536 dimensions, and how can we see 1536 dimensions? Unfortunately, we humans can only see 3 dimensions. So what I'm going to do is I'm going to normalize this embedding vector, and I'm going to create a 3D dimension which we can understand, see and understand, because we cannot do the same with 1536 dimensions. So I'm not going to go into this code. This is available in the Jupyter notebook. Just go and look into this code, how the semantic similarity is running, and how this is plotted using Plotly, and whatever the magic I'm doing with pandas. So I'm just load a lot of embeddings here, and I've passed a query, which is king, and uh, based on this query, again, whatever embeddings which matched in this vector database would be returned in a 3D plot. So this is how everything looks like. So I'll just zoom it a little bit so that you guys can see it properly. Right. So this is my 3D vector data space, and I queried King here, and you can see all these movies which are coming for uh, king query. So once the king is converted to vector embeddings using cosine similarities, all these movies are returned. But if you see very closely, few things like Alice looking through the glass or walking Sleeping Beauty, these are very close. Monkey Kingdom and Lion Kingdom, Lion King is very close. So again, like even we returned all these vector embeddings in 3D space based on King, but again, there are a couple of movies which are very close to meaning in terms of each other. So those are very close in the vector spaces. So for example, if I come here, I can see the coordinates and the score for a movie King Arthur, and so for the a kid in King Arthur's court. So this is how things are plotted in your vector space, and things which have like meanings or semantics or vector embeddings closer into the vector space, they appear very close, and cosine similarity will fetch all these. Using cosine similarity, we can fetch all these uh, and get closer meaning chunks or data for our retrieval. So now we understand how we can retrieve. We kind of visualized also how things look like in 3D vector space. And we now understand how we can retrieve things which are semantically similar from a vector database. Let's move to the final part of this demo, which is the generation part. All right. So now we are on to generation. And again, we're doing the same drill again. We are just initializing everything. We are loading the environment and everything. And I've taken a very simple example here for everyone. What I'm going to do is I've created a database which is called movie index, which is called movies embeddings.index. You can find this in the project repo itself. This is the file. And this is a particularly very large index database, not as like a smaller movie.json which we created earlier. But I'm going to load it in my overall index. And what I'm going to do is again going to create a query, which is called, which is I'll just take a text like story of a warrior who fights for his kingdom. That is my query. I'm going to do the same drills, create embeddings for my query, and then whatever data which I retrieve from my index, I'm just going to do a cosine similarity, figure out what is in my vector database is closer to the query text which I'm just passing, the embedding which I'm creating for this query. And whatever I get, I'm going to fetch top five results, and then I'm going to create a prompt template here. So if you see, I'm just getting the description of all the movies, top five movies which are returned here, and I'm going to pass this description to a LLM prompt. What is this prompt? This is very simple. This prompt is basically a user is looking for a movie recommendation. I'll pass the actual query which we have, and here are the top movie recommendations, which is the movie descriptions, which is generated based on the top movies which we got from the based on the cosine similarity from our vector index. Right. Once we have the data, I'll just pass this prompt to my OpenAI client for chat completions. And once it has the user query, once it has the movies which are returned based on the user's query, it can generate an answer, a recommendation for you. So this is an example how we can generate a movie recommendation system. This is very simple example, but this could be more complex. You can have entire workflows with all the nuances in place. But this is very simple example to showcase how things will work if I want to build a movie recommendation. So I'll just quickly run this. My query was story of a warrior who fights for his kingdom. So I'll just run this, and you first of all got all the movies with the recommendations. We got all the movies for the recommendations. We got Gladiator, we got like Lord of the Rings, we got Avatar, Iron Man. I'm not sure how Iron Man came in this, but you get the meaning, like the context. So we basically, based on this query, it returned these five movies. And what we are going to do is we're going to pass these movies in the prompt, which is again fed to our OpenAI client for the chat completions. So this goes to our I think we used GPT-4 401 Nano for this generation, and this will complete my based on the movie description. So once its movie description is passed to this, it basically goes and recommends a movie. So the assistant says that I recommend starting with Gladiator because it's beautifully captures the story of the warrior, blah blah blah, and yeah, so this is intense action, emotional depth, compelling narrative. So based on your movie and whatever the plot of the movie is, it can now basically generate an answer for you. Uh, so this is something like very domain specific. We kind of maybe our LLM was not trained on. So we were able to go create embedding out of our query, compare with cosine similarity based on of our vector database which we have. We fetched the results. Then the results came in. We fed the list of results to our prompt to an chat completion model, and that model was automatically able to answer your query in this use case. So let's change this query a little bit. Let's get a space adventure movie. Let's see if it's able to recommend a movie using that. And I'll run this again, and you should be able to see some space adventure movie. For example, like we got Interstellar, we got Avatar. I'm not, again, Matrix is not a space adventure, but yeah, in Avengers, like sometimes they go to space. We got Star Wars, which is very popular. So we got all these movies, top five movies, and then we passed it to this recommendation, this LM prompt, and then the prompt recommended the top recommendation, which is the closest cosine similarity. So you basically got Interstellar as a thrilling space adventure with captivating visuals, a compelling story about exploring distant planets to save humanity. So this is how you can build a small a recommendation system using retrieval augmented generation. You can use this capability to get domain understanding, give domain understanding, domain specific knowledge to your LLMs. This could be your internal wiki, it could be Slack or whatever you can train your ground your LLM on, so that it generates more factual recommendations and answers compared to LLM, which may be like trained on something. Uh, LLMs usually have a cutoff date. Now they have like obviously they can do an internet search, and they can search on internet and give you a response. But LLMs are basically trained on set of data, and their overall understandings are limited to that unless they can go to an external data source like using internet search, or a retrieval augmented system, augmented generation system to fetch relevant factual data which it can ground upon. All right. So with this, guys, I'll wrap up very quickly. So this is what retrieval augmented generation is. We kind of looked into how we can chunk various how we can chunk data. A specific document could be JSON file into smaller chunks, how we can pass it to a vector embedding model and store it into database, which is called a vector database. And on the same way, how we can query, we can pass a query, create an embedding out of that query, do a cosine similarity between a query uh, and a and whatever whatever is stored in the vector database, get relevant semantically similar data out of it and fetch everything to get it ready to be passed to a prompt. So which is the augmentation phase, which we pass the relevant context to the prompt, whatever we have retrieved from the vector database, and then it is fed to an LLM, which is able to generate an answer, which is very straightforward, which we just saw, and give it back to the user. So with this, guys, I think I'm pretty much done. Uh, do check out the QR code here. Feel free to pause the video. Feel free to drop a comment, and ask any question offline as well. But do scan this QR code. There are relevant links for these code samples, the Jupyter notebooks, which you can run on local. There are some other code samples available in that code repository. Links to all my work which I've been doing on AI, the newsletter, LinkedIn newsletter I write, and my books I have written. So all those things you can get access to. Uh, with this, I'll just quickly wrap up. Thank you for watching this stream, guys. Feel free to drop a comment and let me know how it went. Thank you so much.